Hey there, in this video I'm going to explain a question I had from a student who had been doing some explorations and noticed that with certain rational functions, if you have the numerator and the denominator swapped like this, from f being x minus 2 over x minus 1, and g of x just being the opposite of that with x minus 1 in the top and x minus 2 in the bottom, we have symmetry between the two functions. And my guess is that the student was thinking that this was some sort of transformation like the ones that we learned where we would put a negative on a function and it would flip across the x-axis, or if we put a negative in a certain place with x, it would flip across the y-axis. Well, there is a relationship like that, but it's not the same kind of thing. So you want to think of this as a separate type of phenomenon that we see, and it really just has to do with the fact of how the numerator and denominator change based on when you plug in x values. So the best way to explore this is to look at each graph and kind of see what's similar and what's different, and also maybe look at some ordered pairs. So I'm going to give you some instruction on things you can do to explore these questions more deeply if you're interested in doing so. I'm using Geogebra to graph these. It is a free software that you can download, or a free app that you can download, and it's pretty easy to use. You type the function into the input bar in the bottom and then press enter, and it'll show up here. You can right-click it and change the object properties, like the name of it, the color, the style if you want it dashed for an asymptote or solid. And then there's some other things you can do too, but those are the basics. And it allowed me to make the picture you see here. And as you can see, I have the function f graphed in red and the function g graphed in blue. And you can tell that there is symmetry right down the middle right here and right across this horizontal line too. Well, the horizontal line is the horizontal axis of both functions. And that's because the degree of the top and the degree of the bottom, in both cases, the degrees are the same, which means that they would have a horizontal asymptote at the ratio of the two lead coefficients. The two lead coefficients in both cases are 1, so 1 over 1 is 1, and we see that the horizontal asymptote is right through y equals 1. And both of these functions will never cross their horizontal asymptote. And another thing that we see is that it looks like there's symmetry between them through this line right here, this vertical line, through x equals 1.5. Now I'm going to zoom in on this and take away the actual functions so you can see, well, actually, let me do another thing first. Let me first show you just the red function. And now with its vertical asymptote graphed and with a dashed line showing where x will never be, well, I should say the function will not be defined anywhere along that red dashed line. Because if I plug 1 into the denominator of this function, I get undefined. So that's why I have a vertical asymptote there. Likewise for the blue, look at the denominator of g. If I plug 2 in there, then I will have 0 in the denominator, which is undefined. So I do have a vertical asymptote right there through that vertical line. So everywhere here on this vertical line, the value of x is 2. Therefore, we have a vertical asymptote through that line, and the function will never touch or cross that asymptote. It has asymptotic behavior on each side, which means it's veering off in a certain behavior. And just to try to understand why this axis of symmetry between the two functions exists, again, let me just take away the asymptotes and put the two functions and then the line of symmetry. So this is where they are mirror images when they're both graphed together at the same time. Everything looks mirror imaged through this point on the x-axis, this line 1.5. And this is because it halfway in between the two vertical asymptotes of each function. So here's the vertical asymptote of my red function. Here's the vertical asymptote of my blue function. 1 and 2, if you average them, you'll get the midpoint is 1.5. So that's, I don't know if that really helps you understand why, but that's true. That's what's happening. So that's why they look symmetric across that when they're graphed at the same time. But they're also not truly symmetric to that because if you just have the red function and you fold along the green symmetry, it won't match up on each side. They're only symmetric together. They make a symmetric picture together. But it's just something curious and interesting. But let's get away from talking about how they look symmetric when they're graphed together and just talk about why the red function is up here on the left while the blue function is down here on the left, and why the blue function is up on the right and down on the bottom. So we're going to put back our horizontal asymptote, and we're just going to notice that the red function stays above that green line in a certain section for x values that are less than 1, less than this horizontal vertical asymptote. And to the blue one, it stays below, but up to a different point, up to where the vertical axis is for the blue at x equals 2. And the red stays below its horizontal axis anytime it's to the right of its vertical asymptote, while the blue stays above the horizontal asymptote when it's to the right of its vertical asymptote. So let's see what the behavior is, how the behavior is different on each of one of these. So let's start by looking at the red. If we just think in terms of x moving left and right, if I move to the left, my x's are approaching negative infinity. If I move to the right, my x's are approaching positive infinity. Another thing to notice is that if I move to the left from negative infinity and I move to the right towards my vertical asymptote, I'm approaching x equals 1. I'm approaching my vertical asymptote. So I can talk about x, what x is doing in these ways. And I want you to be familiar with that because I'm going to be saying it a lot. If I say, as we approach the vertical asymptote from the left, I'm talking about what x is doing. X is getting closer to 1. And then I can talk about what the function is doing while that's happening. So as x approaches its vertical asymptote from the left, or from negative infinity, what is the function doing during that time? So for the red function, as x approaches its vertical asymptote, my function values, the y values, are moving towards positive infinity. And if my x values start going back towards negative infinity, away from the vertical asymptote towards negative infinity, then what is my function doing as that happens? Then my function is getting closer and closer to the horizontal asymptote and then leveling out because it can't cross that horizontal asymptote. On the other side of the vertical asymptote, as x approaches the vertical asymptote from positive infinity, from the right, the function values are going down without bound, and they're going towards negative infinity, the y value. So as x gets closer to its asymptote, its vertical asymptote, then the y values go towards positive infinity. While x is going away from its vertical asymptote towards positive infinity, the y values are getting close to its horizontal asymptote again, but from the bottom. So they're always lower than y equals 1. All right, now we'll see how the g function behaves. So here's my vertical asymptote for g. As x approaches the vertical asymptote from the left, my y values are going towards negative infinity. And as I move away from my vertical asymptote towards negative infinity, then my function values are getting very close to the horizontal asymptote, but staying less than y equals 1. On the other side of my vertical asymptote, as my x values approach the vertical asymptote from the right, the y values are going towards positive infinity, and as I move away from my vertical asymptote towards positive infinity, my y values are getting very close to my horizontal asymptote again, and they're above it. Okay, now maybe we can get a little deeper looking at some ordered pairs. So for the red, remember the red on the left-hand side of its asymptote, let me get that picture back. To the left of its asymptote, remember all the y values were staying above 1. And as I got closer to my vertical asymptote of 1, they were approaching positive infinity. So why is that happening? Well, let's look at the numerators and denominators. For x equals 0, if I plug 0 into the numerator x minus 2, I get negative 2. And if I plug 0 into the denominator, I get negative 1. So the relationship between the numerator and denominator has a quotient of 2, positive 2, because they're the same sign. Then if I get a little closer to my vertical asymptote value of 1, notice that my y value is getting larger towards positive infinity. And this keeps happening. The closer I get with my x values to positive 1, my y values are getting closer to positive infinity. On the other side of that axis, the vertical asymptote, it's not really an axis, it's the vertical asymptote, and on the other side of it, very close to the vertical asymptote, notice that I have this insanely big negative value because it's way down low when I'm very close to that asymptote. But as my x gets farther away from the vertical asymptote towards positive infinity, notice that my y values are also increasing, but at a certain point, they don't increase very much. And you can see that those y values are almost 1, but never quite reaching it. So that's the behavior we're seeing on the left side of the axis of, the left side of the vertical asymptote. The y values are approaching positive infinity, and as you move away from that asymptote, they're approaching the actual horizontal asymptote of y equals 1. On the other side, staying close to the asymptote, I'm at negative infinity, but the farther I get away, the closer I'm getting to that horizontal asymptote. What about for the blue? For the blue, just the opposite is happening. Here's my vertical asymptote, different number, but the same type of behavior is going to occur, just opposites. So on the left-hand side, as I get closer to my vertical asymptote, the y values are staying below the horizontal asymptote, and as I get closer to my vertical asymptote, my y values are going towards negative infinity. On the other side, I'm close to positive infinity, but as we get farther and farther away from the vertical asymptote, I'm flatlining close to 1, but right above it. Now, if you want to be able to do something like this, I'll quickly show how you can do this more efficiently than having to plug in numbers or even type numbers by hand. And you can also do this with a graphing calculator, but I like working with Excel, and I like sharing with students how to do this because it's a very useful system. You can use it for a lot of different applications in your life. So let's learn how to program this Excel spreadsheet to give us ordered pairs and even make it so that we can look at the numerator and denominator separately. Well, the numerator for the red says it's x minus 2 for the red function, f. Well, if I want to find the numerator when x equals 0, I'll put an equal sign, so it'll act like a calculator in that cell. Anytime you put an equal sign first, it'll do a calculation for you. So I can type in 0 minus 2 and press enter, and it'll give me negative 2. I could do that for any x value. I can put an equal sign, then the x value 0.5 minus 2, and it gives me another numerator. However, there's an easier way to do this, or a more efficient way of doing this. You can put in equals, and then instead of typing in the x value every time, I can click on the cell containing the x values that I've already selected, and then minus 2, enter. And if I want to copy that down so I don't have to keep retyping this, now I can do that because I made a relative reference to the cell A2. And if I drag vertically, that reference will change vertically. So let me show you what I mean. Selecting the cell, there's a little green box down on the right, and I can toggle over that until it looks like a black plus sign, and then pull down. Hold my left mouse key and pull down. And it copies the formula down for me. And if you notice right here in the formula bar, when I press enter, each time it goes down to a new row, the row reference is changing. And I can do that for my denominator as well. I can use the x minus 1 and then copy that down to get all my denominators. And then to get my y values, or the function values, I can do the numerator divided by the denominator and copy that down. And what I also did was I just put some highlighting here so that I could clearly see where my vertical asymptote was. For the blue, same thing, except for the values are a little different. And this time I'm going to show it an even faster way. All right, so I'm going to put in equals. For the numerator this time is x minus 1. So I'm going to click on the cell containing my x value, minus 1, enter. Now I'm going to do, instead of copying that down right now, I'm going to do all of these across, and then I'm going to copy all 3 at once. So I'm putting the equal sign, the x value minus 2 for the denominator, and then to get the y value, it's equals the numerator divided by the denominator, enter. And now I can select all 3 of these cells. To select, make sure your cursor looks like a white cross, then hold down your left mouse key and drag. Once you let go and all 3 of those cells are selected, you can go into copy mode on the far right one, and then you can either pull down like you did before, or you can double click. And then I'll just highlight my axis again. All right, so hopefully that gave you some ideas for how you can explore these further. Putting these side by side or on the same graph together, this is what they look like. Notice that with Geogebra, you can type things in one by one, and then you can click on them to make them go away individually and put them back in. So this could be something fun to explore with, as well as doing some formula reference calculations in Excel. So I hope you got something out of this video, and if you're still not sure what's going on with why these things look flipped when you swap their numerators and denominators, make sure to email me your thoughts, and I hope to see you in the next class session. Take care.